Okay, so welcome to the Ireland session. The first speaker is going to be Natalia Chechina, who is from the Herod University in Edinburgh. Please.
Well, I'm going to talk about the design of Scalable distributed Erlang. This is a part of the release project. You can see all our collaborators working on the project. This paper is also a result of a collaboration. So there's a professor called Trinder and a PhD student, Amir, Ghaffari from Rickard University, Rickard and Kenneth Lundin from Ericsson, and Robert Virding from Erlang Solutions. So first I will provide some background information about the release project, about Erlang, then about motivation and challenges, why we want to build SD Erlang, and then the design of Scalable distributed. So first of all, that's the release project, and what we want to do is a scaling radical concurrency-oriented programming paradigm to build reliable general purpose software, massively powerful computing, machine code. So in general, the work is happening on 3 levels. The first level is evolving the Erlang. The second level is our level, that's language level, and the work I'm going to talk today, that's here. And another thing is development of scalable Erlang infrastructure. So Erlang is functional programming language. It is actor-based, it is dynamically typed, it is general purpose. It was developed in Ericsson in 1986 for telecommunications, distributed, fault-tolerant, massively concurrent, and soft shorthand systems. A nice feature of the Erlang language is that its concurrency is handled by the language and not by the operating system. When we talk about the Erlang community has a very strong love and strong passion to the language. And here we need to talk about the philosophy of the language that makes it so attractive. So the first of all, it's share nothing. Processes are autonomous. They're isolated. They don't share memory, and variables are not reducible. And another very nice thing that came from telecommunications, that is let it crash. So we use non-defensive approach, and processes just crash, and other processes are built to not let crash and restart the processes if they're needed. This is distributed Erlang, if we look at the blue rectangular there, these are hosts. A host might have a number or a single node, which is a big Erlang VM. These are yellow things. And then nodes, they may have a number of processes. Erlang is very good in the concurrency, and when we think about the parallelism of one node, it's really an example and good thing to have. Because each node, it can maintain about 2 million processes at the same time. So what's the problem? Why do we talk about the scalability here? The problem is in the transitive connections that nodes have. So when we have 50, 100 nodes, everything is fine and everything works perfectly. They share connections, they talk to each other, they renew global information. But when we go further, we all know that these transitive connections that just don't work. So this is the first problem. Another problem is that when we spawn a process, we spawn it to a particular place. So we say the node, we say the machine, we say everything where we want to spawn it. And that is another problem, because if you have a very structured network, that's not a problem, right? You can just spawn it there and no problem at all. But if it's not structured, then we either need to remember everything, which is not actually feasible. Typical architecture. So the project aims 10 to 5 cores. And it's a thankful work, actually, to predict what we're going to have in 5 years. But to work with the language, to have an idea of what we built the language for, we need to do that. So this is the typical hardware architecture that we expect the typical Erlang problem will use. We think there will be 32, 64 cores that share memory, and we call this a module. We think there will be 4-6 modules that will form a host. So we have hosts here, shared memory, we have clusters here, they form a host. And around 100 hosts will make a cluster. Something like maybe from 1 to 5 clusters will make cloud, and cloud will be connected to each other. So here we also distinguish levels where a process can be spawned. So it can be spawned to a node that on the same host, that's on another host, but in the same cluster, or in a host that's on another cluster, but also in the same cloud, and then another cloud. Scaling. When we thought about the design of the language, we thought about 3 levels. First of all, this is a scalability of persistent data structure. Because if persistent data structure doesn't scale, no point to have a scalable program, it just will not work. The same goes for in-memory data structures. But we think that such structures like Rickard and Cassandra, they will deal with that and we don't bother. Another thing is in-memory data structure. These are mostly at stables for Erlang. And they are maintained by the VM. So as we work on the language level, we don't care. So our level is computation. We shall work with computation, language, and that's what I'm going to talk now. Challenges. Erlang exists already, and it has a lot of users, and they use the language, they love the language. So some of the challenges are to scale the language, but preserve good things that we already have there. These are reliability model and supervision behavior. So scale, but not to lose good features we have there. And another thing is, we want that scalable distributed Erlang to become a part of Erlang distribution. So we want it to be used. It means that we need to please the programmers, the Erlang users who are going to use this. And we have a number of principles that we agreed before we started to design the language. So these are general principles such as working on Erlang level as far as possible, and preserving Erlang philosophy and idioms, not to make the language foreign to the programmers, and minimum language changes. Another thing is reliable scalability design principles. So we want to avoid global sharing. We want to avoid explicit prescriptions and introduce abstract notion of communication architecture. So that's when we talk about different levels, so different nodes, different clouds of the same cluster. And keeping, of course, Erlang reliability model, one of the trademark of the Erlang, unchanged. So the Erlang design, as the Erlang design, it has 2 directions. The first one is that we want to restrict the connections because we have a problem there. And also, we want to have some explicit placement. We don't go to implicit placement directly, but we think that it's better to take one step at a time. So from explicit placement, we go to semi-explicit placement. Network scalability. So we want to group nodes. So nodes are currently have transitive connections. It means that when a new node is connected to a network, and it's connected at least to one node, it immediately becomes connected to all other nodes. So we don't want that. And for that, we introduce scalable groups that we call S groups. And in scalable groups, nodes have transitive connections within a group, but non-transitive connections with nodes of other groups. we thought about what type of, how we want to build our S groups. And we thought about hierarchical or overlapping partition. Partition already exists in Erlang, and it doesn't look it works well. Hierarchical is restricted, and it contradicts to Erlang philosophy, where nodes can be, any node can be connected to any other node. So we picked overlapping. And also, currently, when we use global in distributed Erlang, it means that they have global space. So all nodes replicate data about all other nodes. And we want to restrict that and put it to as group namespace. So, what happens? Initially, we have a network of nodes, and then all have transitive connections. And this is a distributed Erlang. And then we create a new group, G1, for example, node A, that consists of 3 nodes, A, B, and C. It doesn't mean that when a new S group is created that all connections hold. Just when the connections were there, it was quite a mess. But what we might have are short-lived connections. So when nodes belong to a group G1, they may have short-lived connection with other nodes that will be lost over some time, maybe lost. Or we can just disconnect from all other nodes. We also may have overlapping groups. So nodes may belong to more than one S group. And here an example, we created another S group that consists of nodes C, D, and E. And node C belongs to both groups. But it doesn't share information, for example, about node A and B with nodes D and E, and vice versa. And we preserve here the Erlang philosophy that any node can be connected to any other node. So node B can be directly connected to node E, but they don't share any information about other nodes. So these are S group primitives. We can create an S group, we can delete it, we can add nodes, delete nodes, send messages to nodes, and so on. This is just a list, this is an initial list. We don't plan it to be as it is. We plan it to implement the things that are going to use, and we'll see that when we implement language. And the same goes for S group abstractions. We think that we'll need algorithms, skeletons, and behavior abstractions, something like S group supervision and S group master slave. But we expect those abstractions to be visible and apparent when we'll have case studies. So another problem is explicit placement. So we have a process and we want to spawn it, but it's impossible in such a network knowing exactly which node contains what. So we want to have some kind of placement there. We can place a process to an S group. We can place a process depending on the distance. So, for example, on the same host, the same cluster, depending on the level. And the decisions also, so a user can say, I want to place, for example, a process to this distance. And if there are more than one possibility to place this process, then there can be different design decisions there, right? We can use random approach. We can use load balance or something else. And this is a function that we propose that. So it's a choose node, and we have restrictions. The restrictions, we keep them as a list. This is a design decision because we want it to be extended later. So this can be a nice group. You can spawn a process to a nice group on some distance. And then the program will look something like that. So we have a target node. We choose a node. We define a nice group where this process will want to be spawned. And also we say what the distance should be, ideal distance. And then we spawn that process to that distance. So in conclusion, well, this is the design of SDO Erlang. The main two things that we want to implement there as groups, that is to restrict the number of connections we have there. And for that we introduce transitive connection within as groups and non-transitive connections between nodes that belong to different as groups, that don't share the same as group. And also we want to introduce an explicit placement to help a programmer to place those processes. And we're implementing it now, we're working on it. Thank you.
Any questions?
How would you compare your S groups to, say, communicators in MPI?
Communicators, well, I'm not sure, I'm not much communicators at any point. I can compare with, in Erlang, for example, there are global groups and global hidden groups. They're similar to that idea, in that global groups, they also have their own namespace, and they have transitive connections within them. But hidden global groups, they have partitioned networks, so nodes can belong to only one global group. But I can't, I'm sorry, compare with those. I'm sorry.
Questions? No? Well, I do have questions, of course.
That's good.
Which process sets up the networks and creates a group? Because Erlang is distributed, right?
Yes, it
so
is, yes.
which processes create the nodes or specify which networks are connected? In the diagram that you show, I mean, when you have several groups together in a list, which processes create that?
We want we don't want to maintain some global information. So, the thing about Erlang nodes is they have unique names. So, actually, this information it don't need to be kept anywhere. So, if a node creates, for example, an S group, then we can identify which node actually created that S group. So, this information doesn't need to be stored anywhere. So there is no need actually to keep that information. And each process, the process just, if it wants, it creates the S group.
And they communicate it to the rest of the processes, or?
Not to the process, but to other nodes.
Oh.
So, for example, if you create an S group and it contains of A, B, and C, then when node A created that S group, of course, it needs to be sure that nodes B and C know about that. So it will propagate this information and will wait for a response from them whether they agree to be a part of that S group. So that will be decided later, but it's a programmer design decision, and it's I think will be a programmer responsibility to build something sensible from it. We can't introduce a language, I think, that prevents people doing something stupid, right? So we provide some constraints.
We can, but it wouldn't be a particularly useful program.
I mean, with the imperfect language, we can do a lot of stupid things, right? So there is, of course, responsibility for a programmer to make the design decisions for their programs. We can't guarantee any safeness there.
Okay.
Yeah, I had a related question. Can a node create an S group of which it is not part?
No.
Can a node drop out of an S group?
Yes, it can.
So essentially it could create an S group of which it is not part by first creating an S group of which it is part and then dropping out of it.
Well, the thing is that we want to also introduce a master node here. I wouldn't like to speculate much about that because we don't plan to implement it immediately. But most probably what is going to be done is that if a node will not become that S group, the S group will just disappear either.
Okay.
Or it will pass its responsibility to some other node.
Thanks.
Any more questions? Okay.
Thank you.
you.